Okay, let's continue from where we left off. And this time we'll go into parallel connections in KVL. So let's see, new share. Oh, KCL, I'm going to assign this for student practice. And then KVL and parallel connections, okay? So KVL is a little more involved when we're trying to write the equations, okay? First, I'm going to talk about the concept of a loop and a mesh. An electrical loop is basically any closed pathway, okay? Any closed pathway that allows current to flow through. Okay, so electrical loop is any closed pathway that allows electrical current to flow through. Essentially, if you start a point in a circuit and you go around and you come back to that same is you could start at the same point and you end up back at the same point. Okay. So if you take a look at the example on the left, let's say I start at the bottom left corner. If I start at the bottom left corner, I can say this is loop 1. The direction of the arrow does not matter, okay? And then I can also start at the same corner and go around and come back to that same point. In this example, it is labeled as loop 3. So that takes care of those two loops. And finally, if I start at the bottom middle corner node and I go around and I come back to that same point, I get loop 2. Okay, loop 1, loop 2, and loop 3. It's a closed pathway, basically multiple ways of starting at a point and coming back to that exact same point. And that comprises a loop. Now, if you notice, loop 3, which is the outer loop, contains loop 1 and loop 2 inside it. Contains loop 1 and loop 2, right? I'm gonna clear these out. Loop 3 contains loop 1 and loop 2 inside it, okay? And here's where we talk about the concept of a mesh. So a mesh is a simple loop that does not contain any other loop inside it. Okay, a mesh is a simple loop, and a simple loop is one that does not contain any other loop inside it. And so in this example, loop 1 and loop 2 are meshes because they are simple loops that do not contain any loops inside of them. Whereas loop 3 does contain loop 1 and loop 2, so it is not a mesh. And mesh is an important concept that we will look at in chapter 2. Okay, so having established that, let's talk about KVL, Kirchhoff's voltage law. Again, voltage law states is based on the law of conservation of energy. It simply states if you sum up all of the voltages around an electrical loop, they will all always add up to 0. They will always add up to 0. And so the way I apply KVL, and again, the point of applying KVL and KCL is to generate equations. So the way I apply KVL is I start at the bottom left corner of a loop, and I go around that loop, and I add up all the voltages. So if I take loop 1, and I start at the bottom left corner, I have VA, VB, and VC, all summing up to 0. Right? You have 3 voltages in loop 1, A, B, and C. So VA, VB, VC. The polarity of these voltages is already given to us. So I can start plugging in my values. The way I apply KVL is like this. I start at the bottom left corner, and I see the polarity of the voltage that I encounter first. So VA, I encounter the minus sign first. So I'm going to put down a minus sign in front of VA. Then for VB, I encounter a positive sign. So I'm going to place a positive sign in front of VB. For VC, I'll encounter a positive sign again. So plus. So I'm summing up in a clockwise direction. Okay, I'm summing up in a clockwise direction. If I sum it up in a counterclockwise direction, I would still obtain the exact same equation. If I sum up in the counterclockwise direction, I have VC, I have VB, and I have VA. And they should sum up to 0, right? So if I sum up on this side, the first voltage I encounter is VC, and VC I encounter first is minus. I'm going to place minus. Then VB would also be minus right here. Let's use a different color. So summing up in a counterclockwise direction, I get minus, minus, and then VA is plus. So I get minus VC, minus VB, plus VA. And exactly the same equation. Let's take a pause while you think on that. Let me know if you have any questions. Does that make sense? Okay. And again, as I stated, if you have a preferred method of applying KVL or KCL for that matter, you stick with what you know. You don't have to use my methods. All right, any questions? Okay. All right, then let's talk about parallel connections. Parallel connections between 2 or more components are a result of connecting both their terminals together. So both the terminals of components of the components. Okay. And so in this case, if we take a look at A and B both have two terminals. They are connected together at the top and at the bottom. And if both terminals of components are connected together, with break in that they are connected parallel. So A and B are in parallel. The same thing on the right side. You have D, E, and F connected together at the top and at the bottom. And so they are also in parallel. However, C is not. C is only connected at the top to AB, but the other end of C is not connected to AB. C is connected to the top to D, E, and B, but it's not connected to the bottom of D, E, and B. And hence, C is neither in parallel nor in series with the other components. Let's take a pause, think over that. Let me know if you have any questions. Any questions? Okay. And let's look at one example of KVL. In this example, we are given VA 10 volts, VC is 15 volts, VE is 20, and we are asked to find VB and VF. So VB and VF, well, first thing we can see is D and F are connected on the far right, and both terminals of D and F are connected at the top and at the bottom without a break. And so we can state then D and F are both in parallel. And if D and F are both in parallel, they have the exact same node at the top and at the bottom. Parallel connections, voltage remains the same. Electrical voltage is the difference in electric potential between any 2 points. The voltage that appears across D and F is a result of both D and F acting or working at the same time. And so the voltages that appear across those two nodes is exactly the same value. Okay, so voltage across parallel connections always remains the same for every element. Because it is a result of all those elements working together. Okay, and the same time in series connection, the current remains the same. So if I was to apply KVL and I wish to find VB, I can, let's say VB is in this loop and is also in this loop, to the left as well as to the right of B, right? So let's first find VB, then we can find VD and VF. I will start at the bottom left corner of this loop, and I will sum up the voltages in a clockwise direction. If I apply KVL at the bottom left corner, I have three voltages, VA, VB, and VE, summing up to 0. VA would be plus, VB would be plus, VE would be minus, right? Plus, plus, and minus, summing it up in a clockwise direction. I'll simply plug in the values. VA is 10 plus VB and minus of 20 is equal to 0. So VB is equal to plus 10 volts. Does everyone agree? Let's take a pause, think over that. Let me know if you have any questions. Make sense? Then if we wish to find VD, we apply KVL in the second loop, either here or here, and we can find VD. So if I apply KVL in the smaller loop, I have VB, VC, and VD summing up to 0. Starting from the bottom left corner of the loop, minus VB, minus VC, minus VD equal to 0. So I can write VD is equal to minus VB minus VC. Plug in the values. And VB is minus 10. VC is minus 15. And so VD is minus 25 volts. Okay, any questions? I assume students have done this in physics, right? For some students, it might be a long time ago. Some of you might have taken it just recently. But again, these are the three most important techniques that we need to know. Everything else is, derived from these three. And that's why the separate homework for each one, as well as the work. Okay, there are homework based on KCL and KVL, as I stated earlier. KCL, I believe, is due tonight. KVL is due tomorrow. If you have not yet started it, go ahead and get it started. If you have any questions, reach out to me anytime. I'll be more than happy to answer those. Okay. All right, let's take a 10-second pause before I move on to chapter number 2. Any questions about chapter 1? About anything we have learned so far? As we move into chapter 2, we'll start with the basics, but then we will, steadily ramp up towards, new analysis techniques, larger analysis techniques, where students will be required to very quickly identify connections in series and parallel, apply, KCL, KVL, write out equations, and then solve them. Okay, shall we move on? Okay. All right, chapter 2, resistive circuits. And these are all DC analysis techniques, okay? So the first up in chapter 2 is combining resistors in series and then combining resistors in parallel. And then we'll look at circuits where we combine resistors in series and parallel and reduce it down to one single resistance. So here in example A, we have three resistances in series. We can take a look. R1 and R2 are connected at a single node. R2 and R3 are also connected at a single node. There are no more than two connections at each one of these nodes. And so we can state, actually, let me draw it out here. R1, R2, R3. We can state that R1, R2, and R3 are in series with each other. The entire network is in series. And if we wish to find the total equivalent resistance of the outer terminals or between the outer terminals, it is simply the sum of all the resistors in series. There is a derivation. The derivation is from Ohm's law, right? We write out the individual voltages between all three of them and we sum them up. And you can find the total equivalent resistance, REQ, as R1 plus R2 plus R3. Okay, total REQ is simply the sum of all the resistors in that combination. When we say combine it together, this is just purely theoretical. But the physical basis in real life is that, let's say if you have three resistors, all 1 ohm each, 1 plus 1 plus 1, between the outer terminals, you can model it as an equivalent resistance or one single resistance of 3 ohms. Okay, so physically there would be three independent resistors on your circuit board, but electrically speaking, the effect of those three resistors in series is the same as one single resistor worth 3 ohms. Yeah, that's what it means. When we talk about combining, it's a mathematical model. A mathematical model, but it has a physical basis in real life. All good? Okay. Resistors in parallel. Again, there's a derivation based on Ohm's law, but we'll go straight into the equation. The equation is that Req is the reciprocal of the sum of the reciprocals of each individual resistor in that network or in that circuit connection. So we have R1, R2, and R3. And we see at the top, they're all connected together. And we see at the bottom also that they're all connected together. So electrically speaking, it's the exact same node. Even though we see multiple dots in the circuit, this is not node 1, 2, 3, 4, 5, 6. This is simply node 1, and this is simply node 2. In a parallel circuit, in a parallel connection, there's only two nodes. That's it. So if you have any two nodes, all components connected between any two nodes are said to be in parallel, as long as there is no break in the middle. Okay. Take any two nodes anywhere in the circuit. Everything that is connected between those two nodes is considered in parallel. In this case, it's R1, R2, and R3. And if they're in parallel, then the total REQ, total equivalent resistance measured between nodes 1 and 2, is the reciprocal of the sum of the reciprocals of the individual resistors. 1 over R1 plus 1 over R2 plus 1 over R3. When you sum it all up and you take the reciprocal of that sum, you get REQ, total equivalent resistance. Again, I assume students are familiar with this equation from physics, right? There are a couple of things I will point out, okay? If you have only two resistors in that parallel connection, R1 and R2, then the Req for two resistors in parallel is the product of the two divided by the sum of the two. Product of the two divided by the sum of the two. It comes from this equation. If you do 1 over, if you do the reciprocal of 1 over R1 plus 1 over R2, and you solve this equation for only R1 and R2, you would obtain this. Okay, you would obtain this equation, R1 times R2. If you solve this equation for two resistors, you would obtain this equation. Product of the two divided by the sum of the two. Next, if you have multiple resistors connected in parallel, and they all have the exact same value, 1, 2, 3, all the way up to n. N number of resistors connected in parallel, excuse me, all having the exact same value. Then the Req is simply the value divided by n. That's it. It's R over n. And you can try it out. If you have two resistors worth 10 ohms each, the total Req would be 10 divided by 2, 5 ohms. If it's 100 ohm resistors, 300 ohm resistors in parallel, it would be 100 divided by 3, 33.33 ohms. And you can take any value, million resistors, all with 1 ohm each, it would be 1 ohm divided by a million. And that's the second point. And for the third point, I will actually go first to a series connection. Let's say R1, R2, and R3 are all the same value, 10 ohms. What is my Req? What is my Req? Yes? No, series connection. 30 ohms, right? R1 plus R2 plus R3. Sorry, I switched back to the series. But the point I'm making is, look at the value of the resistors, 10 ohms. Look at the value of Req, 30. What is 30 in relationship to 10? Higher, larger. Our brains don't have to think. We automatically know when we add something together, the resulting quantity will always be larger. So our brains are already tuned to that. We don't think about it. But here's what you do have to think about. If you have resistors in parallel, the resulting Req will always be smaller than the smallest resistor in that parallel network. Again, if you have a parallel network of resistors, then the resulting Req will always, always, always be smaller than the smallest resistor in that network. And our brains do not automatically think about that because it's not quite as obvious. So Req, what is happening? Is always smaller than the smallest resistor value in a parallel circuit or a parallel network. So if you are solving a circuit and your resulting value for Req in a parallel circuit is equal to or higher than the smallest value, then you should immediately think that your answer is incorrect and you made an error somewhere. Okay, so it's an extremely important tip for self-verification, for self-checking. Again, Req in a parallel circuit is always smaller than the smallest value in that parallel combination. All right, let's take a pause. Let me know if you have any questions. All right, no more questions. Then let's get into equivalent resistance examples. If you take a circuit like this, typically in electrical engineering, you would see a circuit drawn out with components either horizontal or vertical. And the terminals more likely or more often than not will always be on the left. Okay, not always true, but that's how typically it's drawn out. So these diagrams, which are circuit diagrams, will always have terminals on the left. So the problem on this page is asking, what is the value of the resistance you would measure if you connected a meter between these terminals? Okay. What is the total equivalent resistance you would measure if you connected a meter between these terminals? And so for circuits like these, I would always say you start at the farthest end. So it's example A, I would start at R4 and I would move towards the measurement terminals one step at a time. Okay, I would reduce the circuit one step at a time by combining the resistors from the far end, from the far right. So what do I see about example A? Req is R4 in parallel with R3, which is then in parallel with R2, right? My circuit reduces like this. I'm still going to call this Req. This is still R1. I'm going to call this as R5. R5 is R4 in parallel with R3 in parallel with R2. Make sense so far? Right? Then what can we say about R1 and R5? Are they in parallel? Are they in series? Neither? Anyone? There's no penalty for speaking up. R1 and R5. Series, right? Because they are connected at one node. There are no more than two connections at that one node. So Req is R1 plus R5. R5, we have already established, is the parallel connection of R4, R3, and R2. And that's your resulting Req. And this is what students need to practice a lot. Students need to be adept at manipulating circuit elements, reducing as much as possible, and then applying the equations. Let's take a pause while you write it down. Let me know if you have any questions. Any questions from anyone? Okay. Okay. How about example B? Example B, if I start at the farthest end, what do you see? Farthest end has R4. Okay. What can we say about R4 and R2? They are connected at the top node, right? They're connected at the top node. But is R2 and R4 in series? No, because you have more than two connections at that node. So straight away, you should get into the habit of looking at nodes, counting the number of connection at a node. If you have more than two connections, series is out of the question. There shouldn't be more than two connections or two components connected at a single node, okay? Not connections, but components. Okay, if you have more than two components connected here, it's not in series. Okay, then let's take a look at parallel. R4 is connected to R2 at one end, but the other end of R2 and R4 are not connected together. If that's the case, then they are not in parallel. So R2 is out of the way. How about R3? R3 and R4 are connected at the top at one end. The other end, R3 and R4 are also connected together. So that means, what does it mean for the relationship between R3 and R4? They are in parallel. So R4 is in parallel with R3 because both ends of the respective components are connected to each other. I like to use the term holding hands. They're holding hands together. So R3 and R4 are in parallel, and we can reduce it to one single resistance. So I'm going to draw out the circuit like this. And one thing you'll often hear me state is you redraw the circuit as many times as you need until it starts to make sense. Okay? As long as you keep the original connections intact, you redraw the circuit in any way you want until it starts to make sense. That is something that I used to do as a student. And so I would have R1, R2, and I'm going to do this. I'm going to stretch out the bottom node. Okay, I'm going to stretch out the bottom node. Again, remember, theoretical analysis, everything is hypothetical, everything is ideal. So a tiny dot like this, I'm going to stretch this out like this. Okay, so I've stretched this out. That's just a manner of drawing. It doesn't change the actual circuit. And I'm going to call this as R5. R5 is the parallel combination of R4 and R3. Make sense to everyone? Any questions? Yes. Oh, scroll up. Okay. Here you go. And I'm going to label this node so it makes it clear. So this is one single node, call it 1. All of this is one single node, call it 2. So 1 is still here, and 2 is still here. Okay. And let's call this as node 3. And this is node 3 right here. Okay, 1, 2, and 3. Then since we're starting at the farthest end, we can reduce the circuit even further. I have R1, and then this would be a series combination of R2 and R5. I'm going to call this as R6. And then finally, REQ is R1 parallel R6. Now, I want to make a quick point. When you're solving this for the homework or for the quiz or the exam, you don't have to draw it out as long as you have the equations. You can have both if you wish, that is fine. Or you can do just the diagram and just show it step by step, and you can have the final values in there. So there are multiple ways of presenting your work. You can present it graphically, you can present it analytically, meaning just the equations or just the illustrations, or you can show both, your choice. But the information must be conveyed. This is again another important thing for students to develop while you're still in school, while you're still in college. You develop your communication skills, right? So again, here I have shown both. I've shown you the illustration, and I've shown you the analytical equations. Not complete equations, but get the point. All right, let's take a 10-second pause. Let me know if you have any questions. I will leave C and D for students to practice. And then what I want to do is I want to show you a technique that would work on most circuits. Yes. So the question being asked is, should we or can we draw R1 and R6 together and show it as R7 or REQ? And the answer is student's choice. You don't have to, students don't have to, but they can if you wish to. So that would fall in the category of being thorough with your analysis. So students don't have to, but they can do if they wish. And REQ is of course measured here. Anytime in circuit analysis where you see a quantity being asked, think of it as a meter that is being connected at those points to determine what the value is. So the real life equivalent would be you're taking a multimeter and you're connecting between those 2 points to determine REQ, or to measure voltage, to measure the resistance, or to measure the current. So anytime you're asked to find a quantity, think of it in those terms, right? And the purpose of theoretical analysis is always you want to predict what your real life measurements would be, right? So you would perform theoretical analysis, you perform some theoretical calculations, so you can verify whether your measurements are correct or not. And that is always the point of theoretical analysis. Doesn't matter what field of engineering you're working in. Okay. I want to show a technique that will work on most circuits, especially on the homework problems. Okay. So in this technique, what I do is I draw out my measurement terminals spaced far apart horizontally. Okay. Let's say this is 1 and this is 2. And I'm going to use example B for this. Okay, B. My goal is to draw all the resistors that are there in the circuit, R1, R2, R3, R4, vertically, going from terminal 1 to terminal 2. Okay. So the objective of this method, the objective is to go from terminal 1 to terminal 2, right? Those are my measurement terminals. So my objective is to draw everything vertical. And for this, I'm going to start from the left. R1 is connected between 1 and 2. Right? R1 is connected between 1 and 2. So I'm going to draw out R1 right here. What else is connected to R1? Sorry, not R1. What else is connected to terminal number 1? R2. So I'm going to draw out R2. I'm going to space it a little further apart than R1. Now the goal, as I stated, is to get to terminal number 2. R1 is connected between 1 and 2, so I can simply drop a straight line to terminal number 2. Then R2, what is connected to the other end of R2? R3 and R4. The goal is to draw it vertically, so I'm going to draw it vertically like this, R3, R4. And we just saw, right, R2 is connected to that end of R3 and R4. So I'm going to make that connection right here. Right? And this is 3. Then where is R3 and R4 going? R3 and R4 are connected directly to terminal number 2. And so I'm going to extend the other end of R3 all the way to 2. And that's it. That's the end game. Now all my resistors are in independent branches, all connected vertically. I can combine it together. From here, we can see R3 and R4 are in parallel. We can combine those two together. And then R3, R4 in parallel is in series with R2. Once you're done with this branch, you leave it alone. You come and reduce the other branches in the circuit. In this case, there are no other branches except R1. So you have R1 in parallel with this entire branch, which is what you have at the end on the right. Let's take a pause. You think on this technique. Let me know if you have any questions. This technique will work on most circuits out there, complicated ones. On the homework problem, there are some diamond-shaped circuits, and this technique will work on those. Keep the fundamentals in mind, meaning 1 and 2 are single nodes. Nodes can be a small dot, could be a small dash, could be a very long line. It does not really matter. In this technique, what you're going to do is you take your measurement terminals, meaning 1 and 2, where you're measuring REQ. You draw out 2 horizontal lines spaced far apart. And then you draw out all the other components one by one, starting from terminal number 1. And the goal is to reach terminal number 2. And every single resistor has to be drawn vertically. And then you make the appropriate connections. Also, important point to keep in mind is not all circuits would be reducible manually. Okay, in real life, you will see circuits that you would not be able to reduce manually. You have to find a roundabout way of determining resistance. Measuring equivalent resistance is easy. Doesn't matter what circuit is. You have 1 million resistors all connected like in a big jumble. But you have two measurement terminals. All you do is you take your measurement meter and you connect it to those two terminals. You can measure your resistance. But theoretical analysis is not always possible. In this class, the examples that you would see are reducible. I'm not going to give students any circuits that are not reducible. Okay. And then this technique that I just showed, you can reduce any circuit with that. So the question being asked is whether this technique would work on the Wheatstone, the diamond-shaped circuits. The answer is yes, it will. Oh, where in your physics classes? Okay, okay. And again, as I stated, it's not always possible to reduce all circuits, but most circuits that are reducible, this technique will work. So we are out of time today. And again, remember, chapter number 2, we are going to build on every single step. So it is very important for all students to keep up with every single step. So right now we started with resistors in series and resistors in parallel. Then we took those two techniques, we combined those two techniques together, and we are now applying those techniques to reduce large circuits down to one single resistance. Next class, we are going to introduce a source into the circuit. The goal is to determine the voltages and currents. The technique that we will use is still exactly the same as we just learned, meaning combining all resistors in a circuit into one single equivalent resistance. Okay, so it builds off of very small levels of technique and we build on larger circuits. All right, so we'll end class here today. I'll be in my office later on today until 4 o'clock. If you have any questions, send me an email, stop by. If you can't stop by and you wish to meet on Zoom, just send me an email and I'd be happy to answer your questions. Okay, all right, I'll bid you all a good day and I'll see you all on Friday. And quiz, I will post the announcement just later today shortly. We'll have a quiz on Friday, quiz number 1. Quiz number 0 is 5 points due tonight. As long as the work is submitted and it has the required amount of pins, you'll get full credit, even if the answer is incorrect. Okay, all right.